Hello and welcome. Today, we're going to dive into a question that's right at the heart of artificial intelligence, and really, all of problem solving. It's a big one. How do you actually teach a computer to solve a puzzle? I mean, really solve it. It's not just about crunching numbers. It's about logic, it's about rules, it's about finding that one needle in a haystack solution that fits a whole bunch of different conditions. So how do you translate that very human way of thinking into a language a machine can actually understand and execute?
Well, it turns out there's a really elegant way to do it. There's a formal structure we can use to define these kinds of problems, and that's the first, most critical step to getting a computer to solve them for us.
And that formal structure is called a Constraint Satisfaction Problem, or CSP for short. Honestly, the best way to think about it is like a universal recipe for just about any logic puzzle you can imagine. It always has three main ingredients: the things you need to figure out, the choices you have for each of those things, and the set of rules that you absolutely cannot break.
So let's break down those three building blocks. Because if you can master this framework, you can define almost any problem. Getting this part right is the whole game.
We call this the VDC framework. First, V, you identify the variables. These are the unknowns, the decisions that need to be made. Second, D, you define the domains. This is the pool of possible values or answers for each of your variables. And third, C, you specify the constraints. These are the rules that tie everything together. They're the laws of your puzzle's universe. A valid solution has to satisfy every single constraint, no exceptions.
Okay, that's enough theory. Let's see this thing in action. We'll start with a super intuitive visual problem that's a classic in this field.
Our first puzzle is map coloring. So take a look at this map of Australia. The goal seems simple, right? Color in each state and territory. The only rule is that no two regions that share a border can have the same color. Seems easy enough for a person to do, but how do we turn this into a problem a computer can solve? Well, we use our framework.
So here's how we break it down using VDC. Our variables are simply the regions themselves: Western Australia, Northern Territory, Queensland, and so on. Easy. Our domain is our palette of available colors. Let's just say for this example we have three: red, green, and blue. And finally, the constraints. These are the rules of the game. If two regions are next to each other, their assigned colors cannot be the same. So WA's color cannot equal NT's color. And just like that, our visual puzzle now has a formal logical structure.
Okay, now let's shift gears. We're moving from a visual puzzle to something a bit more abstract. A classic logic challenge that has fascinated computer scientists for decades. This is the n-queens puzzle. The goal is to place n queens, in this case 4 of them, on an n by n chessboard. But here's the catch. No two queens can be in a position to attack each other. Now if you know chess, you know that means no two queens can be on the same row, the same column, or on the same diagonal.
Now pay close attention, because the way we formulate this is really clever. Instead of making every single one of the 16 squares a variable, which would be a mess, we simplify. We make a rule: 1 queen per row. That means our variables are just Q1, Q2, Q3, and Q4, where each variable represents the queen in that row. The domain for each of these variables is which column it sits in. Column 1, 2, 3, or 4. You see what just happened? By setting it up this way, we've already solved the no two queens in the same row rule. It's baked into our definition. So the only constraints we have to worry about now are making sure no two queens are in the same column or on the same diagonal. It's a beautiful example of how choosing the right formulation makes a problem so much simpler.
All right, so puzzles are fun, but the real power of CSPs comes from solving messy, complex, real-world problems. Let's look at something that factories and businesses grapple with every single day: scheduling.
Imagine you're assembling a car. The variables are all the individual tasks that need to get done. Install the front axle, attach the right front wheel, tighten the nuts for that wheel, and so on. Now, the domain for each task isn't a color or a position. It's time. Specifically, the start time for that task. And the constraints, well, this is where it gets really complicated. This is where you define the entire workflow.
And those constraints get very specific, very fast. You have precedence constraints. You have to install the axle before you can install the wheel. That's a rule. You have disjunctive constraints. If two different tasks need the same specialized tool, they can't happen at the same time.
one has to go first. You have resource limits, like maybe you only have 4 assembly stations. And of course, you almost always have deadlines. The entire car needs to be finished by the end of the shift. This is where CSPs go from being about puzzles to serious industrial optimization.
So let's just pause and think about what we've done. We looked at coloring a map, a classic chess puzzle, and scheduling a factory floor. 3 wildly different problems. But we used the exact same language, variables, domains, and constraints, to describe every single one. And that is the whole point. This is the superpower of the CSP framework.
This quote just nails it. It says that by using this framework, you don't have to reinvent the wheel every time. You don't have to design a custom solution from scratch for every new puzzle. You just have to get good at describing the problem. You define the what, the variables, the domains, the constraints, and then you can hand it off to a generic, off-the-shelf CSP solver to figure out the how. It's a massive shortcut.
And the range of applications is just mind-blowing. Creating a university timetable without classes clashing? That's a CSP. Figuring out the most efficient routes for a fleet of delivery trucks? CSP. Designing the intricate layout of a computer chip? Solving Sudoku? Allocating a company's budget? Planning a path for a robot? They can all be modeled as constraint satisfaction problems. The same fundamental logic applies across all of them.
So the big takeaway here isn't just a list of problems, it's the framework itself. Learning to see the world through this VDC lens is an incredibly powerful skill for thinking with structure and clarity, which leads me to a final question for you. Think about something in your own life, planning a vacation, scheduling your work week, maybe even just organizing a project. What everyday problem could you understand better by taking a moment to define its variables, its domains, and its constraints? Give it some thought. Thanks for watching.